In this video, we'll take a look at a single node pair circuit. That's the parallel circuit. The analog to that was the last video where we took a look at the single loop circuit. Single loop circuit was a series circuit that had one single current throughout all the elements in the circuit. A parallel circuit, that analog to current would be voltage, so it'll have one single voltage across the single node pair. So let's take a look. Any number of simple elements connected between the same pair of nodes is a single node pair element. This circuit here shows 4 elements connected between the same pair of nodes. If we look at the nodes, we have one node, a top node, and we have another node, the bottom node. So that's our single node pair. We need at least 2 nodes to form a loop in a circuit. So if we do KVL across, we could do KVL around a loop, but let's choose our KVL where any path between the 2 nodes in the circuit, so any path between our top node and our bottom node must have the same potential difference. So if we look here, this potential difference is the voltage across the 120 amp source. We draw this potential difference VR1, this potential difference V30, and this potential difference VR2. All these voltages must be the same because they share the same pair of nodes. So instead of drawing all these voltages, we can just draw one voltage V, or we might draw, if we label this node A and this node B, we might call this VAB, so the voltage at A minus the voltage at B. So there's one voltage in this circuit, but we have multiple currents in the circuit. So they're all parallel elements. Our definition of parallel is that they share a common voltage across them. So, and again, that common voltage is the exact same voltage. It has the same 2 reference positions, and we'll call that our VAB. So, again, that's voltage across each element must be the same. They're all in parallel. So if we look at the currents in the circuit, we have this current here. That's our 120 amps. And that's between this branch between the top node and the bottom node. We'll draw flowing downward our IR1. We have our 30 amps that is flowing downward, and then we have our 1/15 of an ohm. These are very small resistances, and there's our IR2. So in this circuit we have the 4 different currents and the 1 voltage. So let's see how we can apply KCL, Kirchhoff's current law, and Ohm's law to write equations to help us solve for the voltage. So let's look on this diagram. We don't need to relabel 120 amps, but we'll call this IR1 and we'll call this IR2. So our KCL equation, the sum of the currents into, and we'll do KCL at the top node. We could do it at the top node or bottom. We'll do KCL at the top node. Sum of the currents into the node is equal to the sum of the currents out of the node. So flowing into the node, the only thing we have defined there is 120 amps. That's flowing upward and into this top node. So that's our 120 amps is equal to flowing out. We have IR1. We have 30 amps, and we have our IR2. So we can look at this equation. Well, it's easy enough to bring our 30 amps to this side of the equation, and we have 90. We'll drop our units, is equal to IR1 plus IR2. Well, our KCL gives us one equation, but 2 unknowns. So how are we going to solve for those 2 unknowns? Additionally, what we'd like to solve for, we said, is what is the voltage between these top 2 nodes, or between the top node and the bottom node, and we'll call that our VAB, where we label the top node as A and the bottom node as B. So we want to know VAB, what's that equal to? That's what we're trying to find. Well, we can use Ohm's law to find the voltage. We have a relationship between voltage, current, and resistance, and this voltage is across both of these resistors. So that's KCL in our top node. Let's do our Ohm's law. So for Ohm's law, we have IR1 is equal to the voltage across R1, which is VAB. IR1 is equal to VAB divided by this resistance R1. So it's equal to VAB divided by 1 over 30. So it's equal to 30 times VAB. So now we see why these are such small resistances. That's so we don't have to deal with fractions in this problem. Additionally, by Ohm's law, we have that IR2 is equal to VAB divided by R2, VAB divided by 1 over 15, or 13 VAB, where that AB is our that's 15 VAB, where VAB is our subscript. So if we plug this IR1, that one's IR2, and IR1, that's a 2, back up into our KCL equation. Let's plug it into this one where we've already simplified. Then, with this substitution, we get what? We get 90 is equal to 30 VAB plus IR2, 15 VAB, and then simplifying this equation, we get that our solving for VAB, so VAB is equal to 90 divided by 30 plus 15, 45, or that's equal to 2 volts. And that's systematically using our KCL and Ohm's law, where we've defined each of the currents and we've substituted in for our resistor current the voltage divided by the resistance, because we know the resistance and what we're looking for is the voltage. So we can go back and find these currents. These currents then would be equal to IR1. We can go back and solve. That's equal to 30 times 2, or 60 amps. IR2 is equal to 15 times 2, or 30 amps. We can draw that up there. Let me see. Our IR1 was 60, so this is 60, and our IR2 is 30, and we see flowing out we have 60 plus 30 plus 30, that's 120. That's equals to what's flowing in. So we've done our just our KCL check. Additionally, we can check our power, right? So what we can always do, and I'm going to change the size of this screen for a moment, what we can always do, the sum of the power supplied must equal the sum of the power absorbed. So we see that this 30 amps is flowing downward, and the voltage at the top here is positive, and it's negative at the bottom. So we have 30 amps flowing out of the positive node. So this is absorbing power as long as VAB is positive, which it is. 120 volt amp source is supplying power, and both of the resistors should always be absorbing power, and in fact we solve for that they are. So our power supplied, we have our 120 amps from this source times our 2 volts should be equal to, we can use our I squared R, or we could use I times V. Since we didn't, what we solved for was V, what we'll use for the power absorbed in the resistor, we'll use V squared over R. So we'll use, it's going to be for our 1 over 30 ohm resistor, we have our 2 volts squared divided by 1 over 30 plus our 2 volts squared divided by our 1 over 15. Those are the resistances. And additionally, we have our 30 amp source. So we have 30, and that's absorbing power 30 times 2. So it should be, so 240 is equal to 4 times 30 plus, and that's 2 volts squared. So that's our 4 times 15 plus, that's again going to be 4 times 15, but that's 60. So once we sum these up, that's 120. This is 60, that's 60. So 240 is equal to 240. Check. And we did our check by looking for conservation of power. We could look at one more problem here. Maybe we'll save this other one for class. What's important is being able to also take such a problem and deal with a dependent source. These are already labeled. The two nodes, the top node and the bottom node, the potential difference is labeled as Vx. When we look at this dependent source, that's voltage controlled current source is controlled by Vx, so it's controlled by the only voltage in the circuit. So we will not need to necessarily do another equation for this voltage source because we're trying to solve for what we want to know. Well, this asks for IA, IB, and IC. But before we do that, we should also find Vx. So setting up this KCL equation, or KCL, is going to be equal to, we want to find, excuse me, let's jump back, since what we want to find is IA, IB, and IC. So our IA is equal to Vx divided by 18. IB is equal to 0.1. I'm going to write 0.1 Vx, but in fact these are in the opposite direction, so it's actually negative 0.1 Vx. And then our IC is equal to Vx divided by 9. And again, that theory is Ohm's law, our Ohm's law theory. So now we can write our KCL equation. We have 5.6 amps flowing into the node. Flowing out of the node, we have IA plus IB plus IC plus 2. So we can write our equation to bring that, just simplify, and we have our 3.6 is equal to IA plus IB plus IC. That's what we're supposed to look for. We only have one equation. We have 3 unknowns. So we do have these equations that we just wrote based on what we're trying to look for. So we can plug these in, these 3 equations, and this is our 4th equation, and then we can solve for Vx. Once we solve for Vx, that gives us our 4th unknown. So we have 4 equations, 4 unknowns. We can solve 1, 2, 3, 4. These 4 equations and 4 unknowns, we should be able to solve for IA, IB, IC, and Vx. So I'll let you finish this problem, and we can discuss this in class tomorrow.